Mm. Okay, so it's already also recorded the lessons. So they will continue with your last lecture. So we were talking about finite element method for two-dimensional linear elasticity. Contrary to Jan, I will be writing from whiteboard because I don't have a device, or I have a device, but it cannot project. So I'll be writing in whiteboard. And by the way, yeah, some people came, so you also do it. So essentially, you have this two-dimensional linear elasticity setting, which we have assuming just like a short-time stress, which means essentially that we have three components of the stress of the stress tensor, sigma x, sigma y, and tau xy. And the loads are also defined within that plane. And for this example, what we should say is that we have some kind of boundary conditions. We have boundary condition, traction or stress-based or force-based boundary conditions, which are the loads or this distributed load here. And then we have essential or displacement or kinematic boundary conditions, which is for that part, which is fixed. And so for this displacement-based boundary condition, we denote the domain of this boundary condition by gamma u. Well, for this force-based or stress-based, traction-based boundary condition, we have this gamma p. So that's the domain, the boundary for this boundary condition. And what you can see below, I know that you talked about it a bit. So those are some equations for the problem. So essentially, this means that we need to have some kind of force balance equation. We call it force balance. Because this equation, this one holds for all the points within the domain. Then we have this second one, which again holds for all points within the domain. And that's some kind of material law. Yeah. So there's a material law, and then we have now this equation that somehow enforces boundary condition for the problem. But we talked about it already, so I just want to somehow recall this. Okay, and this is something that I think you already wrote down. But let's do it again. Just to have everything captured on this template. It's connected. Okay, it's right. Yeah, what you can see in this. So yeah, but what you want to do is somehow to describe the energy of the system. And this is and basically we can somehow split it into the part this external energy that is produced by vector displacements. And then internal energy that is also made vector displacements. And so what we start with is this energy that is produced by external forces, and in particular, now we concentrate on forces that are defined on the domain omega, which is like the body. And so now we have we have the body load x underline, which is like a vector field. and it has two components. It's underline overline actually. So this underline means it's a vector. This overline means it is prescribed. Yes, and it has two components: x overline and y overline, which are of course they depend on x because they are on lowercase x, which is like the spatial coordinates in the domain. And you can see that in this figure. So for example, in this case, we have this x, capital X overline, which is the prescribed body load, and this infinitesimal point. And in the other figure, we have this y pointing upwards, which is the body load in the upwards direction. Yeah, and for the energy, for this energy, virtual energy, so it's virtual energy. So this x mean is related to external forces, external body load, and it's related to the body. So this one here, and it will be a function of some virtual displacement delta u, which you can see in this figure here. Yeah. And so what we can do, we can write some kind of double summation here. And essentially, what we can do, we can sum up over all delta x and delta y of the body. So delta x, delta y. And now we need to write down the formula for work, which is produced by this body load. So it will be x overline of x. Yes, so that's this volumetric force. Or yeah, but we need to somehow multiply by something to produce a new force. So we multiply it by delta x, delta y, and t. So essentially what we do, we multiply by volume, so that this result with this product is essentially force, and to produce work, we multiply by virtual displacement, which is delta u. Of x underline. Yeah, so we have force and displacement, so it's work. But this displacement is virtual, so it's spatial. Okay, so that was the first component for this W external. Second component is related to the other direction. And so we can also have plus y underline x underline delta x delta y t virtual displacement of x. Actually, yeah, here I made a mistake, so this should not be here in dU, but it should be dV because we have this direction. Yeah, so that's the other component. Yeah, so that's essentially like simply writing down what should be its virtual work. But of course, what we would like to do is we would like to push this delta x and delta y to the limit. So we push delta x going to some with dx, and delta y goes to dy. So we can derive this using integral. So essentially, what we get now is, yeah, first we see that this E is something we can factor out. So we can write T, and now essentially we have double integral over x and over y, and on this inside is x of x virtual displacement u of x plus y of x virtual v displacement of x. Of course, this is dy dx. Yes. Now we can actually somehow recall that if we do this integration, actually the domain, this domain will be the whole domain will be an area. That will be the area. And if we go back to the previous slide, it will be actually the domain of omega. Yes. So this means that this integral is also t over omega. And now we can actually somehow also simplify or write this into a matrix form. Yes, we can actually write it using du of x, dv of x. So again, these are the virtual displacements. And this is multiplied by x over line x and y over line x. The omega. So that's actually the result for the energy for the virtual work done by this body, external forces. Is this clear? Okay, great. If yes, then we can actually do the same. We can do the same procedure, but now for another type of forces. So now we will prescribe fractions and the boundaries. So those should be denoted by d over line x and d over line y. And as you can see in the figure, so those are again, this is not related to some boundary of the domain which is called gamma p. So it's a boundary with this kind of this kind of boundary conditions. Okay, so again, you can see the figure, and based on the figure, we can somehow try to write down something like this. So again, we have some kind of virtual energy. Again, it's an external energy that is produced by external forces. But not on the boundary. Gamma p. And again, it's a function of this virtual displacement. Yeah, just to be sure. Just to be sure, I think I should have underlined. Yeah. Because what I meant here, it depends on this virtual displacement in this direction, but also the other one. So by this delta u underline, I mean a vector that would be delta u and virtual displacement of just to somehow simplify this underline. So you can write on something similar here. Again, yeah, we need to somehow write down the form like this. So for setting we have in the figure, yeah, we also need to somehow find the value of the forces and the displacements. And now we have a summation. This summation will now be this little slide. What we have is the prescribed load, is P over line x of x, but produce force, we need to multiply it by delta y and t. And again, this works on this virtual displacement, which is this delta u of x. Okay. Then for what we have in the other figure, we have the same thing. Essentially, we have to repeat this. We have t over y of x. The range, so the area is again delta yt, theta yt, and the virtual displacement now is this v direct, this y direction to delta v of x on the line. So again, we can integrate it. Or we can push it actually just delta y go to dy. So what you get in this integral again, it's over y. We lose the outside, and we get e x over line x d u of x underline plus dy x underline v of x underline. Now this will be y. We could do something similar to the x direction, yeah, and to make notation simpler. Yeah, to make notation simpler and somehow avoid this definition of the direction of this y and x, that potentially x direction as well. We will write it in this form. It should be an integral over gamma p, which is actually something that we define also with the components. Again, we can write it down in this kind of form. So we will have delta u of x underline, delta v of x underline, and this is multiplied with dx and dy. And now the domain is this gamma. Okay, so yeah, that was the first expression that we needed. This is the second expression that we need. So those are both related to this external energy. Is this clear? Any question? If not, then let's, yeah.
When we're talking about the force of B, what is the
This B, what is the?
yeah, what is the dash over the B? What is it sort of signify?
Sorry, what is the?
It's dashed over, yeah. What is it?
What does it mean?
I know it's
It's regular kind of stress. Prescribed.
okay. Then why do we put the dash over it?
Oh yeah, because it's prescribed. Yeah,
I
this means that it's prescribed the same as this Y. Yeah, that's like a prescribed load. Yeah, that's external load. It's not somehow defined, and so it is defined with these constants, so or constants, functions, let's say. Yeah, because they can depend on X. But they must be defined. And similarly, if you want to compute some response of a structure, you must define the forces that act on the structure. The same is here, but it's just like written in a more maybe formal way. But this is something that is known a priori. Great. Any other question? If we know, then let's proceed, and let's, so that was directed to this virtual energy due to the external forces. And now, yeah, there's like over here, it should be internal forces, so we are now heading to writing down for the formula or deriving the expression for the energy of the internal forces. So for that, I guess I will remove it. What I have, yeah. So now we can again proceed, just intuitively looking at the figures that we have here and write down similar expression that we had before, but now for the internal forces. Okay, so now this energy, virtual energy of the internal forces of the system, again, they will depend this on these virtual displacements. And again, we can write it down by summing the contributions of these virtual parts. Yes. And so essentially what we can see here, we have three components of the stress and also three components of the shear, which is now actually virtual shear, and which is like the shear induced by virtual displacements. Yes. So yes, and now we evaluate the force and the displacement that would produce this virtual energy. So for this x component of this stress, so we have Sx of x. So to get the force, we need to multiply it by delta y and t. That's the area. So that's the area that is on which this stress acts. And now it also works on virtual displacement. And this virtual displacement is the delta x of x. But we need to multiply, but to produce displacement, actually, we need to multiply this by this is strain. Yeah, so we need to multiply this by the length of this x. The length of this x component of this small slab. So delta x. Yeah, so that's what we have for this first. Yeah, we can proceed with the second component, which is the y component, and essentially the situation there is very similar. So again, we have sigma y of x on the line, and what you can see here, essentially we multiply by volume and then by the strain. So for that component, it will be the same. So it will also be delta x t times the virtual strain in y direction and delta y. So again, this produces the volume. And then the third part will be the shear. And for that, you can write it down. Again, a similar formula. So x, y, yes. There is something fishy here. Yes, indeed. This is underlined. Yeah, so x, y, x, again, delta x, delta y, T and virtual. Yeah, with this delta gamma x, y, x on the line. Great. I will just close the doors. Close the door, this is okay. Great. So now, once we have this, we can again write down an integral form of that. So we again let this delta x go to very small delta x, and then y goes to this very small delta y. And again, you're going to have an integral. Again, we can factor out t outside. T, let's say that the outer integration is over x. The inner integration is over y. And then inside, what we will have is this. So it will be sigma x d epsilon x plus sigma y x d epsilon y x plus tau x y of x delta gamma x1 of x, and now we integrate over dx, sorry, dy dx. And so again, we can somehow simplify this. The simplest form will be now that we have integration over our domain omega. And what is inside is now this virtual strain, let's say vector, or tensor, but now it's vector actually in this notation. It's transposed, and the stress vector, and actually both of them somehow depend on x, and it's d omega. So that's the final form. Can you read it? If not, we are, yeah, I'm happy if you move. Because, yeah, I don't have way to write that. So, again, this is something that is important to resolve. Is this clear to everyone? Is there any question? For this? Yeah, and if not, then we can proceed. We can proceed. Yeah, maybe what I should have in the beginning, but I know that you wrote it down with Jan last time, is why do we actually derive these energies? Because in the end, what we'd like to do is to write an equation, which is the virtual energy of external load in the domain plus this virtual energy of the external load on the boundary. And of course, this must be equal to the internal energy. I usually wrote it down without this dependence on delta U, but it's obvious because we already derived it in this way. So this is something that we want, that is something that we need in few dozens of minutes. Okay, So if this is clear, then we can proceed. And somehow we will step aside now slightly and talk about finite elements and how to use these formulas for deriving finite elements for plane sets. So I guess you already have some experience with finite elements. So just to recall, if we will be solving discretized setting of these energy formulas. Yeah, we will not solve them directly. Instead, we will solve discretized setting. So we will have an approximate solution. And so what you can see in this figure gives some kind of division of the domain of Vega into smaller pieces, which we call elements. So in this figure, you can see that we have, okay, I'm some missing numbers, right? So we have 12 finite elements. Those are denoted with these numbers inside squares or rectangles. Then, and these elements are defined by position and numbers of their nodes. So you can see that, for example, element 1 is defined by node number 1, 2, 8, and 7. Yeah, the ordering of these nodes is done in counterclockwise order, which is important thing, because when we derive somehow the expressions of, for example, the stateness matrix and so on, it depends on its ordering. So we have this kind of ordering of the nodes for each of the element. And of course, to solve a problem, we also need to define boundary conditions. And essentially, we need to know what is degree of freedom and what are constraint degrees of freedom. So essentially, we somehow prescribe some kinematic boundary conditions, which are contained in this constraint degrees of freedom part, and then the other nodes can move somehow freely, and so those are degrees of freedom. And then, of course, we have flows. Okay. And so, if I'm not mistaken, you already did some derivations from 1D for 1D, for example, truss element. So today we will try to somehow extend this to two-dimensional setting. So in this one-dimensional setting, 1D element, yeah, you would have some element that starts here and ends here, and this is defined by x1 and x2 coordinates. Yeah. And for that, I think you defined a local coordinate system of the element that starts in the center of the element. Yeah, so 0 is here. So this is 0. Okay, so x1, x2. And so this x1 will be minus L over 2. And this x2 is L over 2. Yeah, so that's probably something that you did for this one element. And then and then you also define mapping that somehow maps this kind of general elements, like general element with general dimensions, into a setting where the length of the element is 2. And again, we have coordinate system that has 0 in the middle of the element and -1 and 1
and the other at the borders of the element. And for the mapping, yes. For this element, you also define shape functions or basis functions. Should I recall what does it mean? Or yeah. So basis function is something that is used to approximate the displacement field. And essentially what you do in finite elements is that you have the energy balance formed that you wrote just a few minutes ago. And the unknown there was this virtual displacement, which is like some kind of function. But to be able to solve the problem, we somehow do an approximation. We say, okay, this virtual displacement will be sum of n vi, where this is like the base. This is so okay. So this will be your element I. Let's do it in this way. Yeah, so we will approximate somehow the displacement with this form of displacement. And so what should this basis function look like? It's for this one-dimensional element. Yes. For this one-dimensional element, we will define like two basis functions. One of them is like this. So that's a function that is value 1 in this first node and 0 in the other node. So one we call it 1 and 1. 1 means 1 is the index of the node where the value is 1 actually. Then and 2, the shape function like this. So we get 0, 1, and this is again less than the element. And so for that left setting of this one element, the shape function, so this basis function, have the form 1 over L times L over 2 minus X. And the other one will be 1 over L over 2 plus sorry. There's a typo here. First correct. Which should be like this. Let's check it. Let's check it. So if we plug minus, if we plug L over 2 here, we get 0, which is this point here. If we plug minus L over 2 here, we get 1, which is the point here. Yeah, so that's this shape function or basis function. And for the other one, we have something that is somehow symmetric. And then you derived or you use the mapping. And the mapping is that, okay, you say that one said that X will be over 2 multiplied by psi. And now this psi is in the domain -1, 1. And then these basis functions in this one case, which you already did before, so that's why I'm not deriving them. I'm just somehow writing them because it doesn't make sense to derive it again. So 1 minus psi and 1/2 over, so 1/2 times 1 plus psi. And again, we can check that if we plug 1 here, so that's now that part, we get 0. And if we plug -1, here we get 1. So that's kind of mapping from this element with general length to element which has predefined length -1, predefined length 2. Okay. So, okay, so that was somehow recalling what we already did. And now for this 2D element, we need to have these basis functions defined also similarly in the sense that they should be 1 only in the corresponding node and 0 elsewhere. But now we have actually 2 dimensions, not only 1. And what we will do is essentially we can define a function like this in both the dimensions and then multiply them. Yes, and that means if I will do a product of these. If we do that, we will always, depending on which function we would somehow, which combination we will take, we will always end up with 1 point out of these 4 here that will have value 1, and the other will be always 0. Yeah, because essentially what we will be doing, I'll try to plot it somehow. Yes. So if we say that this is on the x direction, and this is y direction. So let's say that we use this basis function for the x direction, and it will be function like this. So this will be the first one, and the second one will be like this. And then we can do a product with another pair. Now we will define these functions for the direction y. And as a consequence, we will get a pair which will look like this. So let's see the first one. And the second one will be like this. And so, of course, now if we do product of that function with that function, it will be 1 at this node, because we have 1 times 1 is 1. But in this case, in this node, we have 0, because this is 0. So we will have something, we can write down something that is like 1 over L. Or maybe let's do it in this form. It's simpler to work with. Yeah. So for one node, you can write down so n1 over half 1 minus sine, and we multiply it by the same shape function, but in the other direction. And in the other direction, we will define a coordinate that will be sine of theta. Yeah, so now we will have this is now sine, and this is now theta. So we have to multiply by 1 over half 1 minus theta. And so we can check if we actually take this element here, and this coordinates of the node number 1 are -1, 1. So if we take this -1s and plug it into this expression for this first basis function, we have 1 over half times 2, 1 over half times 2. So in the end, we get 1 in the node number 1. Is this clear? If not, I can try to explain it somehow again. Yeah. The idea is that we need to have functions that are defined on this domain of this square element that we have. And these functions So we are interested in the values of these functions at the nodes. Yeah. And function n1, this basis function 1, should behave in a way that it has value 1 at the node number 1 and 0 value at the remaining nodes. And this is how we constructed it. We constructed it as a product of this one-dimensional basis function that we use for class elements. Okay, so that's n1. Then of course we have n2. Yeah, I should also write down it's a function of this psi and eta. These are here. So for this shape function 2, we have again 1/2 and 1 plus psi times 1/2 1 minus eta. For this n3, we get a function of psi and eta. We get 1/2 times 1 plus psi times 1/2 1 plus eta. Of course, I can simplify it because this 1/2 and 1/2 result in 1/4. And then we have N4 of C eta is, and I will write it down really simplified way, 1/4, 1 minus T, and 1 plus eta. Yeah. And for these functions, you can check that they essentially match the setting we have in this figure and the ordering of the nodes that we have here. Okay, so those are the shape functions. But we did this kind of substitution or mapping so that we modify the domain of the element from this XY system to psi and eta system. And because we did this, and because we also have the energy, which are some integrals that depend on x and y, we will also need to do substitution there to be able to work with the system. So we need to know what is the relation of this dx, dy, and d eta and d psi. And so for this, we have to start with this expression here. And so we know d of dx is essentially the psi of dx d over d psi. This is just the same thing we spent. Yes. This side here can be rewritten in when we have psi equals to 2 over L of x. Now we just somehow rewrite it. So we differentiate this psi over x. And so what we get is 2 over L d over d psi. And now if we somehow flip it, we get that 2 over L dx is equal to the side, or maybe even better, dx is equal to over 2 d psi. Check. Yes, so that is now for this one-dimensional element, but we can also use it for this two-dimensional setting. But for this two-dimensional setting, we need to write down the same thing for the other component, but the procedure is exactly the same. So we will end up with dy is over 2 d theta. Okay, so this is the effect of the substitution in the integration. When we will do the substitution in the integration, this is something that you will need to have. Right. So essentially, this is somehow what appears in this slide. We have these elements. We are originally defined in this domain where the nodes are with coordinates x1, y1, x2, y2, and so on. But we map it onto a different domain, which has strictly defined coordinates. Why do we do it? It's actually because of numerical integration. Again, I think you did it already, and this Gaussian integration, and somehow it's very convenient to have predefined domain and fixed size domain. So that's why we do mapping. Okay, so now you can see how this basis function actually look like. So you can now see that I did apply, and this first year function is indeed 1, and the node number 1 and 0 elsewhere. I mean, at the other nodes. And the same goes for the other basis functions. Yeah, and actually this figure somehow compresses what I try to draw here for this one-dimensional basis functions. How do we come up from these basis functions to these ones? So this is somehow hidden in this figure as well. Maybe this is more intuitive. Okay, and of course, due to the nature of these shape functions, they are bilinear. That means we have product of two variables there. Okay, so essentially this is what we already did. This is actually the result that we obtained by doing the tensor product. Great. Any questions before we proceed? No? Then again, I will erase what I have here. As I already said, and as is visible in this figure, why did we talk about these basis functions? The reason is that we would like to somehow approximate these virtual displacement fields by something that is easier to work with. And what is easier to work with? Essentially, we have some type. We define this. We approximate this virtual displacement as a product of these basis functions and values of this virtual displacement and nodes. Yeah, that essentially means that we reduce the number of variables in the problem. So instead of like having continuous, instead of having functions as the design variables, because otherwise you need to find finally functions and solve the problem. But with this thing, we say, okay, the functions will be within that family, which is the family of these basis functions. And the function will be controlled by the value of the displacement and the nodes of the element, which I would say is reasonable, because we can control somehow the quality of the result by, say, by defining the mesh. Okay, so but from this figure, it's important is that okay, we have this delta u x, let's say, let's give it x underline, delta v x underline, and this is equal to some kind of shape function matrix, which will go n underline for the element, and that's the matrix we have here. Yeah, so it's a matrix that has some components. It depends on x and 1. So it depends again on x. Yeah, this is multiplied with these virtual displacements. Now I use this index E just to be sure that we are talking about the element E. Yeah, so this is this virtual displacement of the element E. These are shape functions or basis function matrix of the element E. And the form of that matrix is the one that is written here. So essentially it's a matrix that has these components n1, n1, n2, n2, n3, n3, n4, n4, and the remaining entries are 0. And so what does it mean? So it says that this first column is related to this yeah, it's related to this. So in this multiplication, it's actually in this way it's it's something, yeah, it's about different. So we actually if we multiply this, you would have a sum. It would be n that one, the displacement here would be n1 delta u1 plus n2 delta u2 plus n3 delta u3 plus n4 delta u4. So essentially here we will have sum of the virtual displacement in one direction, and the other one is sum of displacement in the other direction. So those are our components. Okay. Now, so that was the basic. Now we can go back again to these virtual energies that we had already. And here we start with again with the external energy or the energy, virtual energy due to external forces. So delta W external now it's ready to be element E. And we will starting with this body loads again. Actually, for this slide, I think I don't have to write it down because yes, only some parts. So let's talk about this slide. So the expression that we have here, yeah, is something that we derived in the beginning of the lecture. That's the very same form of the energy. So the virtual displacement will prescribe the loads and we integrate over the domain, and then we find out like the omega here in the end. And now what we do, okay, we replace this virtual displacement by this approximation that we assume for these virtual displacements. That's what we wrote down there. That's what we use this guy here. Just to be consistent, yeah, sorry, I was not really keeping focus on notation. So this U underline, be consistent with that notation in this lecture. This should be D. Yeah, so we have some known displacements. Sorry for this. Yeah, we have some known displacements. To be consistent with this, we need to have this G. So those are the virtual displacements. And underline, let's say, because it's vector. It is. Okay. So we insert this into the expression. And after doing that, first we can observe that these virtual displacements, virtual nodal displacements, are just some values, constants. Yeah. So they don't depend on x. So on x or y. So we can put them in the front of the integral. And so this integral is then approximated in this way. What we get here is this virtual displacement of the element. This is transposed because we substitute n dv, or we substitute this. So we insert this instead of this delta u, but this was transposed. So if we do the transpose, then we have b delta d transpose and e transpose. So we switch the order in the transpose. So that's why we get this transpose here. And then again, is t integral over domain. And so again, this basis or shape function matrix, which is a function of these spatial coordinates x. Then this matrix x underline overline, which is again this body load vector, which is a function of lowercase x, which is the spatial coordinate. And we integrate over the domain. And now, for the guy here, we can try to somehow evaluate it in a matrix form. And so essentially here, let me make it so this is basically what we know by this F. Omega, yeah, so we know that we have by this F omega. Also will be this F omega on this element. Underline. And this F underline omega element. It is now an integral over the domain, yeah, over the domain omega. So again, we can expand this domain to x and y coordinates. So it can be minus y over 2 y over 2, where, just to recall, but you can see it in the figure, this Ly is the dimension of this element in the y direction, as Lx is the dimension of the element in its x direction, or length of the element in its x direction. So the outer integration is over y, and the inner integration is over x to minus x over 2, x over 2. Then we have this expression here, that we already found out. So, and e of x underline over line x dx dy. But as we already heard, it's convenient to use different coordinate system to use a substitution into this psi and eta system. So we do the substitution, and for that I should not have to erase what I have here. Yeah, but I have the result, so I will just write it. So we already had the dx is equal to Lx over 2, d psi and dy is equal to Ly over 2 d theta. Yeah, so we do the substitution. And now the integral will become, so we're going to integrate in the domain, which is now -1 to 1. -1 to 1, and the outer integration and the unit integration is again from -1 to 1. And now we have n shape function of everything the element is a function of x and eta. Yeah, I forgot to switch here actually. Yeah. We are going to again have this x. Now this is function of psi and eta. And the inner integration is over the psi, the outer integration is over the eta. But because we did the substitution, we need to account for changed weights or changed. We need to account for the substitution, which means there will be some value here. And the value here will be x y over 4. And essentially, we replace with the x by this guy here, with y by the guy here, and that's what is the xt and the eta. And in front of that, we add it up with this constant here, x and y over 4. And I forgot this t here, so it should be like this. X and y t over 4. And so also we can spot already that this x and y over 4 is actually, so let's say that this guy here is actually the area over 4 times t, or it's actually the volume of the element over 4. So this is something we can compute very simply if we change the variables. And now we are ready for the Gaussian integration. So any questions before we proceed? Yes, and we already have an example here for this integration. So let's look at this. So we're setting this as follows. So we are asked to determine the magnitude of equivalent bundle forces for body load, which is constant, but it's defined in this symbolic way. So there's components x over line and y over line, and this is constant over the element. And we are asked to find out how does the force vector look like. Of course, what we will need to do is to use Gaussian integration. We'll try to somehow hide this. So we essentially start from this formula here. But for this integration, we will use Gaussian integration. And in this setting, this is constant, and those are linear functions. So it's sufficient to just use the V1 or this, V1 or one Gaussian point to the V1 Gaussian integration. And so we can write down this for the particular setting as this V, so this volume of the element over 4 times, and now we do the Gaussian integration in 2 dimensions. So what does it mean? So it essentially means that instead of, so in 1 dimension, it was like for this 1 point, the integral of x dx will be written as some weight w, or it's wq, and multiplied by the value of the polynomial in particular point. So f at particular point, which will be psi q, and this would be the value of the integral in 1 dimension. And we have sum over the points. So if you want to, I don't know, whatever number of points you want to have, in our case, it's 1. In 2 dimensions, it essentially means that we need to do an outer loop over this. So in 2 dimensions, we will have f x y dx dy. And so now we have integration. We will have f w this r in the outer index, So we have wr. And now there's an inner part which is w q f. And now this f will be evaluated as 2 points, or as 2 coordinates actually. It's evaluated as a vector because it's now it has 2 dimensions, so we need to supply 2 coordinates. So it will be psi q and eta r. So that's how this Gaussian integration works. How that Gaussian integration works into D, and you can already spot it down written down here. So that's what we do. And the Gaussian integration. So that's why we get this outer summation over R equals to R1, 2. Let's do it this way. So because we are doing now an example. So it's integration for points Gaussian points 1 to 1 because 1 is sufficient in our case. And then there is this weight W R. And then we have the inner part, inner integration Q1, 1. We have the other weight WQ. And we need to evaluate this shape function matrix or this matrix of basis functions. We need to evaluate it at these points. So you will evaluate it and theta q and theta r. And as before, we have transposed, so we need to keep it. So we need to keep it transpose. this OGA is multiplied by this prescribed body load x. So that's the idea, and now we need to elaborate it. It might seem to be complicated, but it's not really complicated. So, to simplify it a bit, we have only one point. Yeah, so we have psi and eta are just both equals. There's a way to figure out. So all the points are 0 and all the weights are 2. So the WQ and WR will be 2 and 2. Yeah, so those are the things that we need to plug in. So indeed, you get V over 4 is WR, WQ are also 4. So we have this. So we can actually calculate it out, for example. And then we have summation over these shape functions that we need to evaluate. That we need to evaluate at the points psi 1, sorry, at the points psi and eta, and these points are 0. So did I miss something? Let's see. Okay. Yeah, I will just this x here. Okay, so now let's check what are the values. What's the value of, or what are the values of these basis functions at this point 0, 0. So let's say that it like this. For example, 1 minus c 1 minus eta, that is the first one. If I'm not mistaken. If you put minus 1, yeah, it gets 1. That's the first one. So if you insert 0, so you get 1/4 of 1 and 1. So it's 1/4. And you can also easily see that if you see the signs here, it does not matter. It will be always 1/4. Yeah, so this is equal to v over 4. No, so it's actually right. It's actually v because these 4s cancel out. And then for this matrix, we get the values 1/4, 0, 1/4, 0, 1/4, 0, 1/4, 0. And then here we get it's transpose 0, 1/4, 0, 1/4, 0, 1/4, 0, 1/4. And we multiply it by x over line and y over line. And so the result that we get is indeed not what we see on the slides, because there is something missing. But what we get, yeah, I will erase this one part. What we get is this v over the volume of the element over 4. We can factor it out, this 1/4. And then we get the vector. And this vector will contain indeed, yeah, it will be transpose. It will be x over line, because just this multiplied by that plus this multiplied by that. This will be x over line in the first row, Second row will be y overline, and so on. X overline, y overline, x overline, y overline, x overline, y overline, and that's it. So if you would think about this, what does it mean for the element? We have an element. That element is some kind of node that we denoted by x and y. So it means that for that component, we distributed 1/4 to this node, 1/4 to this node, 1/4 to this node, and 1/4 to that node. And for the y component, we did the same. Right? Because those are related to the x direction, and those are related to the y direction. So in a sense, it makes sense that the result looks like this. Any question? Perhaps we'll proceed. Oh. Yes. And essentially, we can use the very same procedure for the other force or the other external force energy. So I will erase this. Unfortunately, I think this is the place when I will stop because I'm teaching also after this session, so I cannot really prolong it. Okay, so we have this E, W, external, and now this is on this gamma P boundary. And again, we are talking about this element E. And again, if we go back, we already derived the form the energy will be this virtual energy will be T multiplied by integral gamma on the one over boundary gamma T, the virtual displacement. At point X, this is transposed, P overline, actually underline is now vector, X underline, D gamma. So that's the energy we had in the very beginning. And we do the same thing. So again, we replace this virtual displacement function by the approximation that we made up. So we say, okay, if that guy will be approximately shape function matrix element, again, this is function of x, multiplied by some virtual node displacement d. And from that, what we get again, this is something that is constant, so we can put it in front of the integral. So we have t virtual displacement in the nodes transpose, and inside of the integral, again, we have integration on the boundary, shape function matrix of x p of x d gamma. So that's what we end up with. Yeah. I wrote this because it's not entirely equal. We do the approximation. That's why I wrote this kind of implication. Okay, so now we have this, and what to do with it? I think best would be again to show an example, and especially in this case, it's somehow revealing how that actually works, because now we have integration on the boundary. At the boundary. Okay, so the setting now is, again, we have this kind of element, 1, 2, 3, and 4. And we have Px and Py defined at this edge, at this right edge. And that's the edge to 3. And our goal is, again, these are simply constant over the edge. And again, our goal is to find out what will be the force vector related to that energy. So again, this would be some F gamma T. F gamma P E. So, question is, what is now this integration again? We are integrating at the boundary, but what does it mean with respect to this over here? So what does it mean? What do we integrate actually? So we are in the edge to 3. So we should be integrating here. Yeah? And that means at that edge is defined by x being x over 2. So this is constant. So it does not make sense to integrate over it. But we'll be integrating in that direction. So y is now actually an integral from minus L y over 2 to Ly over 2. And so this will be now our integration domain. Yeah, so we for this vector f gamma p is t times the integral over the edge, which is minus e over, or sorry, minus Ly over 2 to Ly over 2. And what is inside? Inside is the guy here. So that's this shape function matrix E. But now this is explicitly evaluated at x equal to Lx over 2. So Lx over 2, so this is fixed. And the second argument is y, because there's no integration domain. Okay. Again, I guess I forgot to transpose here. I'm very sorry. And here it's the same again. I shouldn't transpose. So we have this. Indeed. Yeah, we have this vector here, so let's write it down this way. Px and Py. Now explicitly this is Py. So next step is again doing the substitution to the different coordinate system. Yeah. Indeed, so it's T. Alright, so now we will integrate it on this different domain. So it's from -1 to 1. We modify this shape function matrix. It will be n, e, but now in these natural coordinates. So instead of Lx over 2, we'll have 1. Because this one corresponds to 1 in this different system. And the other one, y, is the other coordinate, which is theta. Transpose dx, y. Now we are doing the theta. But of course, we need to count for the substitution. So, still remember, so it's going to be y over 2. Again, you can look up in your notes and be derived. It's the number is like this. So it's t and y over 2 and theta. Okay. And so what remains is actual evaluation of that integral. And again, we can use Gaussian integration or Gaussian quadrature. So we get t and y over 2. And now essentially we have 1D Gaussian integration. So we only need to look at, again, the shape functions as different. So we need to look at the different shape functions, evaluate it at this single point, which will be 1, and for the eta we take 0. Yeah, so we have a sum, or we do have to write a sum. We have VQ, we have VQ, WQ, WQ, and then this shape function matrix E is evaluated 1, 0. This is constant actually, and this is constant, we could put it outside. Yes, Vy. And so this is the integral. The solution for the integral. And the solution. What's the solution for the integrals that is? So, as I said, the only thing we need to do is now evaluate these basis functions at these 2 points, or at these 2 coordinates. So, how do they look like? So, we can either write it down, or I can write down the result. I don't know, it's up to you. What should I do? I mean, let's write down the first function and then put the other ones onto the section. It's 1/4 over 1 minus sine 1 minus eta. The other one was 1/4 1 plus sine 1 minus eta 1/4 1 plus sine 1 plus eta 1/4 1 minus sine 1 plus eta. So those are the four shape functions. I'm going to make a mistake. Hopefully not. So, but now if we would insert value 1 for the first coordinate into these shape functions or basis functions, we indeed get that this one vanishes. Yeah, this will be always 0, and the same for the last one. Yeah, so those two will be always 0. And the only non-zero elements are these 2. Okay, so it's t and y over 2 multiplied by 2, which is the weight. And now we have this shape function matrix. So The first one is 0. We already did that, so we know that this is 0. So these 4 entries are 0, because this will be the N1 and 1. So that's why we have 0. For the last and for the second one, we insert 1 here. So we get 2 times 1, which is 2. So 2 over 4, so 1/2. So we get 1/2, 0, 0, 1/2. For this one, we again insert the same. So again, this will be 2. This is again 1. So we again get 1/2, 0, 0, 1/2. And the last one is always 0 because this guy is 0. And multiply by the x, dy. Oh no. So of course, these 2's cancel out, but this division by 2 remains. So we get t ly over 2. And then we get the vector. I will just try to do, I will write it as a row vector and do a transpose. So the first entry is 0. Yeah, first entry is 0. Second entry is also 0. For the first entry, we have 1/2 of px. So 1/2 is here, so we have just px overline, py overline, px overline, py overline, 0, 0. So that should be the result. And so again, if you think about it, what does this result mean? It means essentially that we have this Ly, so we take this P, let's say Px component, we evaluate the resultant force, which is Px times Ly, because the length of the edge, times 2, which is the thickness. We divide it into 2, so we split it into 2 parts. We put 1/2 here and 1/2 here in this x direction. For the y direction, we do exactly the same. So again, we distribute it equally. But it is distributed equally only because those are constant. Like if these are functions, then of course it may not be equal. I mean, if the distribution, for example, is like this, and it makes sense to have a different value here than here. Okay, yeah, sorry, I need to end right now because in 5 minutes I start something. Yes.
What's the WQ?
I will just